But the second last speaker of the conference is going to be Mandelshtam, and she's going to tell us about multi-species, zero-range processes, and modified Macdonald polynomials.
So thank you. So thank you so much to the organizers for putting together this amazing conference. And thank you to all of you for sticking around for the last session. So I will be talking about modified Macdonald polynomials and their relationship to a certain particle model from statistical mechanics. And this talk is joint with Arvind Iyer, who is here, and James Martin.
Sorry, can you do louder?
Louder? How's that? Not too loud? Okay, perfect. All right, so we've already seen several wonderful talks and posters about Macdonald polynomials, so I won't be going into any detail or even defining them for that matter. So all we need to know is that they are symmetric functions in parameters q and t that generalize some other special families of symmetric polynomials. So here's an example of one. So they are indexed by partitions. So this is P221. And as you can see, its coefficients are rational functions in parameters q and t. And one might ask, why would I be studying polynomials that look like this? So the way that I got interested in Macdonald polynomials is that they have this very deep connection with statistical mechanics model called the ASEP. So this is a one-dimensional particle process that's very well studied in probability theory and in stat mech. So in the type A case, this is a model on a circular lattice. And because we have no particles entering or exiting, we just fix the content of this on this lattice, and we just let the particles hop right and left, and we let this process run for infinite time. And the question we ask is, what is the stationary distribution of the process as we let time go to infinity? So by which I mean, what are the probabilities of encountering any given configuration at infinite time? So we have particles of different species, so they're going to be labeled by integers, and our convention is that the larger labels correspond to stronger particles. And the partition lambda tells us that we have one particle of type 3, 3 particles of type 2, and 1 particle of type 1. And all possible states of this Markov chain are just weak compositions with n parts, where n is the number of sites on the lattice, such that when we rearrange them in decreasing order, we get lambda. And so we're going to read the state clockwise, starting from the topmost particle as our convention. So we consider the final particle to be adjacent to the first one. Okay, and we have some dynamics on this model. So adjacent particles can swap places with a certain rate that depends on a parameter t, where t is between 0 and 1. Okay, and this very cool result from not too long ago says that if we want to look at the partition function of this model, so the partition function is the physics term for the sum over all of the unnormalized stationary probabilities of the model. So this is a specialization of the Macdonald polynomial p lambda, when we set all parameters equal to 1, except for the parameter t, which is corresponding to the hopping rate of the process. Okay, so now we want to know what are the combinatorics that can explicitly describe this connection between the p lambda and the probabilities of the ASUP. And there's a very beautiful combinatorial model that interpolates between the probabilities and the Macdonald polynomial. So I will very briefly describe this model. So these are called multi-line queues. So let's fix lambda to be the set of particles. So it's a partition. And let's fix n to be the number of sites of the ASUP. So a multi-line queue is an arrangement of particles on a cylindrical lattice with n columns and of height equal to the largest particle type. And we also have a pairing of this particle, which means we pair the particles in rows above to rows below so that we have strings of particles that all end at row 1. And then the pairing is going to give us a labeling. So the strings of length 3 that start at row 3, they all get labeled 3. The strings that start at row 2 all get labeled 2, and so on. And then each multi-line queue, so every arrangement plus pairing, is going to correspond to some state of the ASUP. So we get that by just reading off the labels from the bottom row. So here it's 3, 1, 0, 1, 2, 3. And that gives us this weak composition alpha, which corresponds to this state 3, 1, 0, 1, 2, 3 of the ASUP. And each multi-line queue is associated to a weight. So I won't go into the details of this weight function, except I will try to give an idea of what this parameter t and the parameter q are doing. So the parameter t is keeping track of particles that are skipped by the pairing process. So for example, when these two particles of type 3 are paired, they skip over the particle of type 2, so that contributes to the t. And then here's another one where the pairing skips over another particle. And the q parameter looks at pairings that are wrapping around the lattice, because remember, the lattice is a cylinder. And when we put all of that together, the x monomial is just looking at the content of each column. So we have 2 particles in column 1, we get an x1 squared, 2 in column 2, x2 squared, and so on. And finally, we can represent this multi-line queue by a tableau, because we all love tableau. So my tableau is in French notation, because that makes it easier to understand how we associate diagrams to tableau. So we are mapping each string to a column. So for example, the blue string maps to this first column with the blue integers by recording the position of the corresponding particles in each row. So this blue string has a particle in column 2, then column 6, and then 6. So we have a 2, 6, 6 in the filling. Okay, and so let's recall that this theorem by Cantini, De Heer, and Wheeler that tells us that the partition function is a specialization of the Macdonald polynomial. So now the unnormalized stationary probability of a state of the ASUP can be computed as a sum over all multi-line queues whose bottom row is the state tau. So if we look at the set of all multi-line queues with the bottom row equal to tau, then and add up their weights in parameter t, we get the stationary probability. So if we sum over all of these unnormalized probabilities over all possible states that rearrange to lambda, we get the partition function. So that's just the sum over all multi-line queues of type lambda n. And so our contribution with Sylvie Cortell and Lauren Williams was that we show that we get the full Macdonald polynomial by summing over this set of multi-line queues with these enhanced, with this enhanced weight function, where we also keep track of the content and the wrapping statistic Q. Okay, so now that we have the first part of the talk, let's move on to the modified Macdonald polynomials, which is what my talk is really about. So these are a combinatorial version of the p lambdas that we get through a formal operation called plethism, which I will get into on the next slide. So here are a couple examples of these. So I have an error here. I think this is supposed to be 221 instead of 21. So as you can see, they have positive, so their coefficients are polynomials in Q and T with positive integer coefficients. And not only that, they're also sure positive. And they have many other remarkable properties that we've already seen some examples of in several other talks. And so my goal is to get an analogous construction for these modified Macdonald polynomials using objects that are similar to multi-line queues by interpreting what plethism means on multi-line queues. Okay, so another look at plethism. So formally, what this means is we take the expression in the bracket, we expand it as a formal sum, and then we take the terms in that expansion and we plug them into the symmetric function. And because it's a symmetric function, we can choose which order we put these terms. So I'm going to group them so that all my x1s come first, followed by my x2s, then my x3s, and so on. And so remember that in order to get the Macdonald polynomial in finitely many variables, x1 through xn, we want to sum over multi-line queues with n columns, where the columns are labeled by x1 through xn. So if we want to get this, we need to sum over multi-line queues with infinitely many columns, where these columns are labeled by these labels. And so, yeah, so this is just a regular multi-line queue with infinitely many columns. And now what I'm going to do is I'm going to compress it. So I'm going to put all of my particles in the x1 block just in a column labeled x1. The x2 block is in a column labeled x2, and so on. So as you can see, I'm now allowing multiple particles in each cell. And also, notice that I'm sending t to t inverse to go from p to h. So I am reversing the direction of my pairing lines, because now I'm keeping track of the particles that are not being skipped. Okay, so what we get is multi-line diagrams with multiple particles allowed per site. And this was conjectured by Sylvie Cortell, Jim Hagelin, Sarah Mason, Lauren Williams, and myself. And then we proved that this works with Arvind and James a year later. Okay, and so again, we're going to represent this multi-line diagram as a tableau where we just map strings to columns like so. And so notice that the weight of a multi-line diagram in the xi's is just counting the content within each column, and that's going to correspond to the content of the filling. So we have 6 particles in column 1, and here we have 6 ones, and that corresponds to x1 to the 6. Also, the skipped particle statistic is now going to translate to a statistic on Tableau, which we call Q inversions, which is just a triple of boxes in this orientation where the entries are increasing when we read them counterclockwise. So here's an example of a skipped particle and the 3 corresponding cells. And then here's another one. So this is another Q inversion triple on the Tableau. And there's a total of 6 of them. And so our theorem is that if we sum over all possible fillings of this shape lambda prime with the statistic of Q inversions, then we get the modified Macdonald polynomial. And the major index statistic is the same as the one in the Hagelin-Heyman-Lur formula, if you're familiar with that. OK, so now we ask, what is the particle process that these diagrams correspond to? And we're going to do the same projection of just looking at the bottom row to see what the particle process is going to do. And the process is called a multi-species totally asymmetric zero-range process. And its states are multi-set compositions with n parts, where n is the number of columns. OK, so here's a slide about this process. So zero-range processes in general are a well-studied particle process from statistical mechanics. So they were introduced by Spitzer in the 70s. And in the type A case, again, we have a circular lattice where at each site we can allow any number of particles. And the dynamics are the following. So a particle of type L can jump to the right if we're reading clockwise with a rate that depends on the site number from which it jumps. So that's the xj inverse, and a parameter t to the power of the number of particles larger than it at that site. So zero range just means that the rate of hopping only depends on the site where you're hopping from. OK, and similar processes to these have been studied by this Japanese group, and our version that we're looking at was, as far as we know, studied by Takayama. OK, and so our result is that if we want to compute the unnormalized stationary probability of the TASERP, then we just have to sum over all of the multi-line diagrams whose bottom row corresponds to the state tau with this Q inversion statistic. And as a corollary, we get that the partition function is a specialization of the Macdonald polynomial at Q equals 1. And our proof is by explicitly constructing a Markov chain on the Tableau that projects to the zero-range process. So I will very quickly explain this Markov chain. So we have our Tableau, and each cell in the Tableau is equipped with an exponential clock. And when the clock goes off, so for example, the clock went off for this cell, we take the maximal contiguous increasing chain above it, and then we increment all of those cells by 1. And in the multi-line diagram, this corresponds to taking that portion of the string of particles and just moving everything 1 cell to the right in the diagram. And it turns out that the stationary distribution of this enhanced Markov chain on the Tableau has the distribution given by this Q inversion statistic on Tableau. OK, and this projects to the zero-range process. And I will very quickly tell you about a couple applications that we have from the connection with Macdonald polynomials. So we can get explicit formulas for certain observables using the H's. So for example, if we're looking at the current, so the current is the number of particles traversing an edge in the limit, and this is given by this explicit formula with Macdonald polynomials corresponding to a single column at q equals 1. And similarly, we can look at densities of particles at a given site, and this is also expressed using these column Macdonalds. And what's remarkable about this is that these quantities are actually symmetric in all of the variables except for the site at which we are computing the probability. And this generalizes to looking at fixed content on an interval of sites, so those probabilities will also be symmetric. Is this a joke? Okay. Okay, good. Okay. So I think my time is up, so you can just read what's up here. And thank you very much.
All right, any questions for the future FPSAC chair here?
So do you have an idea about removing the T and actually allowing particles to move backwards in the zero-range process, and what that might mean for the symmetric polynomial side?
So that wouldn't be, do you mean, oh, so the question is, can we introduce parameters or change parameters so that particles can move in both directions in the zero-range process? So we haven't thought about that, but that's a very good question. So it would probably involve introducing a third parameter that allows hopping backwards. So yeah, that's a good question. Thank you.
So I saw how you got the Q interface corresponded to skipping. What did the Macdonald match correspond to?
Oh, it's okay. So the question is, what does the Q statistic major index correspond to? So that on the Q. So that corresponds to pairings that are wrapping around the Q. So when you look at that on Tableau, that's precisely descents.
So it's like a charge almost.
It is actually a charge, yeah. It is a charge.
Can I ask a follow-up question?
Mm-hmm.
So is there like a nice operation on multi-line Qs that transposes the partition and maybe switches the statistics by any chance? Or just transposes the partition? Like how do you do a transpose in a multi-line Q?
I only have an idea. So the question is there a way to transpose a multi-line queue and get something meaningful? So I only know of what this might look like in the t equals 0 case, so for the Q Whittaker. But otherwise, I have no idea.
In view of the time, any further questions can be asked later. And let's thank Olja again.